Okay, so hi everyone, let us begin with the week 5 tutorial for the magnetism and superconductivity course. So week 5 lecture materials are mostly based on these different statistical models of these magnetic systems like Heisenberg model, and then exchange interaction, ferromagnets, antiferromagnets, etc. Those things are mainly discussed, right? So we'll be solving again 10 questions in this assignment, and hopefully this will come as useful in solving your actual assignment for the week. Okay, so let us begin then. So I hope you can see my screen properly. So this is the question number 1. Let us read the question and then try to solve it. Okay, so question number 1 is, if H is the Hamiltonian for a two-spin system, then the Hamiltonian is written something like this, where H spin equal to minus half J S1 vector dot S2 vector, where the symbols have their usual meaning, and Sz total equal to S1Z plus S2Z is the Z component of the total spin. Then what is the value of the commutator bracket of H spin, that is Hamiltonian total, comma Sz total, that is the total spin along the Z component. Okay, so you have to choose one option for the answer. Now let us try to understand the problem first, that the system is consisting of two spins, and the two spins are denoted by that spin vectors S1 vector and S2 vector, right? And this is the typical Hamiltonian form for the two spin system, minus half J S1 dot S2. Now Sz is the Z component of the spin. So Sz total is the total system's Z component of spin, and Sz1 is basically the spin number 1's Z component value of the spin, and S2 is the second spin Z component value. So you have to calculate the commutator bracket value of the Hamiltonian and the total Z component of the spin. Now after you have understood the problem, let us try to solve it. So because it is a two spin system, let's say the two spins are as denoted in the question, S1 vector and S2 vector. So now because it is a vector, it can have all three components x, y and z. Now we are interested in the z component in the problem, because it is given that the z component of the first spin is S1z and second spin is S2z, and the total z component of spin is given by the sum of both of them. So the Sz total equal to Sz1 plus Sz2, right? Now and also the Hamiltonian for the whole system is given by H spin equal to minus half J S1 vector dot S2 vector, right? Now what do you have to calculate is that the commutator bracket of Hamiltonian comma Sz total, right? Okay, so now basically this means that we have to take a commutator bracket of minus half J S1 vector dot S2 vector, comma this Sz total is written as Sz1 plus Sz2. Now we have to decompose term by term and take each commutator bracket separately to solve the whole answer. Now just notice that here this S1 and S2 are vector components, so we have to take a dot product of the vectors. That means we will be multiplying the components term by term, like the vector dot product as it should look like. So it will be like S1x x2x, and because it is a dot product, so x cap dot x cap becomes 1. So it is just the components multiplied as a product, S1x dot x2x, then plus S1y S2y plus S1z S2z. So it is nothing but the dot product that we have written in the component decomposed form, right? So this is well known from any mathematical physics or vector idea. And the second part of this commutator bracket is already in component form, which is like S1z and S2z. These are not vectors, right? Now we can decompose each term separately to calculate the whole commutator relation properly. So because minus half J is a constant term, so we can take it out as a common term outside, and other terms are taken in a separate bracket. So remember, here the second bracket I am using for a common bracket, and this this third bracket kind looking bracket is basically your commutator bracket. So do not confuse it like a normal bracket. You have to follow the commutator relation when you use this bracket. Okay. So now let us break this whole thing term by term. So first of all, we have taken out the constant, which is j by 2. Then we take out each term separately, which is like the first term is s1x, x2x, comma the second, so this term and this term we are taking first. So this is s1x, x2x, comma s1z, right? Sorry, this will be your commutator bracket. Then because you have a plus term, another term, so you can take this term and then this term together. So it will be like s1x, x2x, comma s2z. And similarly, you can continue with the other terms on this part of the summation also, like this term with each of these two terms together, and then the third term with each of the second two terms together. So let us write those terms completely in the commutator bracket form. So it is s1y, s2y, comma s1z, plus taking the second term with y, that is s1y, s2y, comma s2z. Similarly, for the third term here, for each of the terms, we will again get another two commutator brackets, which is like s1z, s2z, comma s1z, plus s1z, s2z, comma s2z, right? Now, you have to first know about some basic commutator standard relation between the spin operators and its components. So we know from quantum mechanics. So from quantum mechanics and spin operators, we already know this fact that we can write spin commutator brackets like this, that this is si comma sj is equal to I h cut sk, where this I, j, k are basically meaning x, y and z component in a particular order. Like it always has to follow particular order to have a plus sign here. So some of the times people take just assume h cut equal to 1 and just directly write it at as I is k. Or you can also keep h cut, whatever is the is suitable for the given problem. But mostly in some textbooks or some problems, people just assume h cut to be 1 for the problem to be simpler. Okay. And you have to understand that this I, j and k should be taken in particular x, y and z order. Like you have to always go like x, y, z, or y, z, x, or z, x, y. Okay, so this is the order you have to follow. Otherwise, if you go like z, y, then you will be having in a opposite rotational, like you will be going in a opposite order. So then there will be a minus sign in the commutator bracket final result, right? So I think these things you are already familiar with. So basically what I am meaning to say is that you have to always go like this: x to y, y to z, y to z, and then z to x. So always this rotation of the arrow, right? So this is basically what? This is basically your clockwise form. So then if you always go in the components in a clockwise form, then only you will have a plus h cut sign here. But if you like, let's say you go in the anti-clockwise manner, like say in the opposite direction, let's say if you take sx and sxz together in a commutator bracket, then you will be having sy with I multiplied, but there will be a minus sign because this will be a reverse order. So for reverse order or anti-clockwise order, there will be a minus I. So the sign in the commutator bracket right hand side will be negative, and for the clockwise order of the components, the sign in the commutator brackets right hand side will be positive. That means is that if you take sx comma sy, you will be having I sz. We have assumed h cut equal to 1. But if you take sy comma sx, so basically you are going in a anti-clockwise order manner. So then you will be having minus I sz. Okay. And similarly, if you take the other components, like if you say y and z, you will be getting sx. Okay, so basically if you take sx and sy and sz, you will be having, so y and z going in this clockwise manner, so you will be having I sx after that, But if you take sz comma sy, so this order is very important in a commutator bracket. So you may not think that sy and sz are the common components. So if you take them in any order in a commutator bracket, both of them will not lead to the same result. So there will be different results depending on the order of the components. So y and z will give you isx, but z and y will give you minus isx. Similarly for sz and sx, so basically you are again going this kind of a clockwise manner. So we'll be having isy in a positive side on the right hand side, but sx comma sz, so you are again going in a counterclockwise manner or anti-clockwise manner. Then we'll be having a minus sign of minus isy. So these are the commutation bracket relations standardized for the spin component. So these are already known from quantum mechanics. So these are called commutator bracket relations of spin components. Okay, right. So we will have to use these when we decompose each of these commutator brackets on this line and then try to solve each of them one by one. So first of all, you just have to break those terms one by one. So you know probably from the commutator bracket idea how to deal with this product forms in commutator. So basically you take s1x first on the left side and then put the other two in a commutator bracket. Like you take s1x multiplied commutator bracket of s2x comma s1z. Similarly for the other term, because it is a product, so there will be another term where this s1x comma s1z will be a separate commutator bracket, and on the right hand side a product multiplied with s2x will be remaining. So like this, from each of the commutator bracket terms, because there is a product present, you will be having two separate commutator brackets with no separate product present, right? So you have to decompose it in the simplest form so that you can finally use the quantum mechanics standard commutation bracket relations and solve the final answer. So we'll be having that and solving this one by one. So this is minus j by 2. So the first thing will be like, as I said, so first of all take the second bracket, common bracket, s1x common on the left and then s2x comma s1z. So this is s1x in a product from the left and then x comma s1z, right? And the second term will be plus s1x and s1z in a back bracket and s2x on the right hand side. So it is like plus s1x comma s1z and s2x remains outside the bracket. Similarly for all of these terms we will be following the same. So just be very careful and write these separately by yourselves, because I can also make some mistake in any line, so that you can later on point it out by yourself only. Also it will be helpful if you just put the line from where you have to calculate right on top, so that it is easy to see each of the terms, so that you don't make any mistake. Because if you just make any mistake in placing just a single component, the result will be different. So you'll have to be very careful. In this case I have just written this combination bracket relations in between, so it is a bit inconvenient for you to maybe look every time to the upper, like go back to the previous line and then check and see. So I'll just like copy it from the I have written in a separate notebook, so you can also do that. You can write on your own in a separate notebook and then check each term by term if I am writing it correctly. Okay, so let us go let us continue with the further terms. So what will be the other terms? So the first two terms we have already given. Then the terms will be like, let us go back. So it is s so this is s1x comma s2z and then s2x on left remains out. So this is s1x x2x. Wait, I have already probably taken the term. No, sorry, I have taken the term for s1z. So this is like s2z plus, now s1x and s2z comes together and s2x remains on the right. Similarly for the third commutator bracket in a product form, this is s1y, s2y and s1z. So it will be like s1y, s2y, s1z plus then again S1y and S1z and S2y remains outside. Also the last term is not the last term, we are probably left with two more terms. So we have already covered 1, 2, 3, 4, 5, 6 terms. That means each of the commutator bracket product producing 2 terms means we have covered 3 commutator bracket product terms. So 1, 2, 3, up to this we have covered. Then we have to take S1y, S2y and S2z. So we will take S1y, S2y, S2z plus S1y, S2z, S2y. Fourth term is completed. Then this term, this is S1z, S2z, S1z. So it will be like first S1z keep outside, S2z, S1z, plus then take this S1z together with the second term and keep S2z outside. And the last term will be S1z, S2z, comma S2z. So what will be like is that S1z, S2z, S2z plus S1z, S2z. This S2z in the product keep it outside, and the bracket will be completed because there is a minus j by 2 term common on the left. Now we have to choose very carefully, separate term by term. First of all, let us clear it out that you cannot take a finite value in a commutator bracket where you have two separate spin components. Let's say this spin commutation brackets are only valid when this all sx, sy, these actually means that this is from a single type of spin, only the components are different like x, y, z. Then only this type of commutation relation is valid. But you cannot go on like you cannot take two different spins like S1 and S2, and you cannot take their components in a commutator bracket together to have a finite value. Like you cannot, if you take S1x and S2y, so it will not lead to ISZ because then they are two separate spin components, right? In this case there is only a single S, that means all are not so do not get confused. I am talking about components. One thing is that I am talking about if they are of the similar spin or not, and the second thing is that if what are the x, y and z components of the spin. So if S is a single spin, then we can play around with the commutation bracket relations for the x, y and z components of that spin, like in this commutation brackets relations I have discussed with you. But if you have two different spin systems, like you have two different spins S1 and S2, and you have separate components for each of them, like S1 has also S1x, S1y and S1z, and S2 also has S2y, S2x and S2z. But you cannot put them in a commutation bracket together without having the zero value. So always this kind of a system, when we have a two different spins, whatever their components are, irrespective of that, if you have two different spins present in a commutator bracket, so the relation will always give you a zero value. So this is a standard thing that we should follow around here. So let us just first discard those component in the commutator brackets where two separate spins are present. So those will automatically lead to zero value, so we'll just ignore that. So let us check it out. So the first term is obviously S2 and S1, so it will be like 0 from the commutation bracket. Second term will not be that because both are S1. Third term both are S2, so it will be non-zero. But the fourth term is again S1 and S2, so it will be 0. Again the fifth term, so it is like so this is 2 actually, right? So this is 2. So this is 2 and 1, that means it is 0. 1 and 1, that means non-zero. So not non-zero, we'll discuss that separately. So but first of all, let us just check out whether they are of the same spin or they are from the different spin. Different spins are already taken to be 0. So this S1 we leave it out. S2 we leave it out. S1 again giving a 0. S1 giving a 0. This is non-zero, this is non-zero, and this is again 0. So then up to this it is covered. Then just let us see that whatever terms we are left with, how can we get the value from there. So like the second term is second term we left out, like S1x comma S1z. So here you have to use the commutation bracket standard relations. Like S1, both are S1, so it will be having a perfect commutation bracket relation, not from different spins. but the order is like x first and then z. So you are going, if you are going zx, then you'll be having a plus I sy, but here you are going s1x comma s1z, so it will be like minus I, h cut is taken to be 1, remember, and minus I s1's y component, because it is in a counterclockwise manner, and this s2x remains as a product on the right hand side, so this is s2x. Similarly, for this term, you have first of all this s2x comma s2z, so both are s2, so commutation bracket relation is valid, but again you have the like order going as x first and then z, so it will be again a minus sign, so it is like minus I s2 y, and there was a s1 x multiplied, so just multiply it. So here the order will not matter because this is a simple component to component product, so this is not some vector product or some like there is no commutation relation that is coming here, so here the product, the order will not be that much important, so you can just take it in any order. And then this term you have y and z in s1, so y and z means you are going in a clockwise manner again, so it will be like plus I s1x, and the second term remaining is that s2y. Okay, so then this term is again s2y s2z, so it will be like plus I s1y as it was on the left hand side, and then this will be leading like s2x. Similar manner, this term if you calculate, it will be like s1z comma s. So now here comes an interesting point, that these last two terms will be 0 also, because I have already told you that you can only have this xyz commutator bracket relation from a non-zero as a non-zero finite value if you have two different components like x y or y z or z x, these kind of things. But if you have both x, both y or both z, even if they are from the same spin, the commutator bracket will give you 0. That is why here you can see that both are from s1 but both are of the z component, so it will be 0. Commutator bracket with a similar component thing will always give us 0, and similarly here also both are from spin s2, that is valid, but both are from the z component, so this commutator bracket will also give us 0. So this is 0 finally. So what terms we are left with is that mainly is that minus j by 2. So now let us check it out, whatever terms we have. So it is s1y s2x. If you look at just this term, this is also s2x and s1y but with a plus sign. So these two terms are from opposite signs but equal value, so this will be cancelling out. Similarly, you have here s2y s1x with a minus I sign, and here you have s2y s1x in a plus I sign. As I told you that here the order will not matter that much, but let us for this sake, you can just see that the terms are same, right, of opposite sign. So this will also be cancelling out, and you will be multiplying a 0 term with minus j by 2, which makes the whole result 0. So your answer is 0, and you can check that this is probably the option number 3 is the answer. So let us go back and tick mark the answer. So this is option number 3. We have calculated correctly that our answer is 0 from the commutator bracket. So hopefully this is clear. Then let us move on to question number 2. Question number 2 says that if the exchange integral is denoted by j, which one of the following statements is false? Okay, so whichever is the false statement, you have to pick that out. So let us read the options. So exchange interaction j leads to j greater than 0 in Heisenberg model. Second was that super exchange interaction leads to j less than 0 in Heisenberg model. Third is that indirect exchange interaction leads to oscillatory values of j in Heisenberg model. And fourth is RKKY interaction gives j less than 0 in Heisenberg model. So the options are mostly based on all Heisenberg model, and you have to choose whatever the different signs of values that the exchange integral j chooses for the depending on the type of interaction, like if it is an normal exchange interaction, if it is a super exchange interaction, whatever is the sign of j, or if it is a RKKY interaction, then what is the sign of j. So these kind of things you have to know. So this is a conceptual question. So let me just write a little bit that So we are talking about J's sign. So J is the exchange interaction strength, or it is also known as exchange integral, right? Because J term comes here, that if you look at the Heisenberg model's Hamiltonian. So Heisenberg model is a statistical model that successfully described the ferromagnetic systems. Mostly it was first utilized for, and later on it also was calculated for, it was also used for antiferromagnetic systems, but mostly ideally it was started, or it was demonstrated, explained for the ferromagnetic system explicitly. So here in Heisenberg model, the Hamiltonian H is written as minus J sum over Ij. This bracket means that we are talking about the nearest neighbors Ij, and then Si vector dot Sj vector. So this is the case. Sometimes there is also a half sign in front of it, so that you do not double count each of the term. Because this Si and Sj vector multiplication, these are two different spins, Si and Sj, but the condition is that in the summation this I and j should always be terms which are nearest neighbor to each other. That is why you have put them in a bracket like this. And also because you should not double count a term two times. That means you cannot you cannot go on like s1 dot s2 and then again use s2 dot s1, because that is basically a double counting. In dot product, s1 dot s2 is same as s2 dot s1. So that is why to have a double counting, people add a half factor in front of it. But this is the basic Heisenberg model, and there is also field term. If you just take it, that this is minus h I then Si. So this is the separate spins values Si. Both, all of the components are summed up. I means different spins like S1, S2, S3, all of the spins. So here I and J are the spin values, which can be like 1, 2, 3, etc. integers, up to n if there are total n number of spins, right? So, and H is the external magnetic field, and J is your exchange interaction strength. So here J is basically the term that actually gives us the idea or information about what is the interaction that is happening in between the spins. So one part is that how the spins are reacting when an external field is applied on them, how the field is applying with the spins. This is the second term, which is a very common term. But what makes the Heisenberg's model crucial is that he included the first term in the model, where not only the spin's interaction with the external field is considered, but also the inter-spin interactions, like the spins which are nearest neighbor to each other will also interact with each other in some way, and that will also influence the whole system's dynamics, its energy levels, etc. And that is why this term becomes very important. So this tells you the interaction between spins themselves, and because they have to be nearest neighbors, because otherwise the effect will be not that much prominent, because only the nearest neighbors can actually prominently and conveniently interact with each other, right? So this is the idea. Now you are asked about the question that first option, if you remember, is that was asked that if that your J value is greater than 0 for exchange interaction. So this is basically a general idea, is that mostly, as I said, that Heisenberg's model was first model for ferromagnetic systems. So it was generally modeled. So the general Heisenberg model is, if it is nothing specified in the model, then you have to assume that it is the general model which was first demonstrated for ferromagnetic systems. So you have to take that it was generally first modeled for ferromagnetic FM systems only. So if there is nothing specified, you will assume that the system is a ferromagnetic system. That means obviously you know that for ferromagnetic systems J will be greater than 0. But why? We can also explain that from this form, that ferromagnetic systems means all the spins are parallel to each other. So if the system is ferromagnetic, that means at the ground state, all, or when it is a ferromagnetic state, that is it is much below its transition temperature, Curie temperature Tc, then all spins are, this is the parallel sign, parallel to each other. That is why it defines a ferromagnetic system stable state. And if all spins are parallel to each other, that means all spins could be either all up, could either be all up, that means all SI values are plus 1. Okay, not plus 1, sorry, my mistake. So I meant to say that all SIs are positive. Because it is a up spin. Okay, and if or the other option is all spins are down spins. Okay, so then all SIs are negative. And you can generally in Ising model on this kind of things, SI sometimes these values are taken as this SI is plus 1 if they are all positive, and SI is minus 1 if all are down spins or negative. So as usual, if you have this SI dot SJ dot product where you multiply the two components, two spins, neighboring spins SI and SJ, and you know that both of them will always be parallel to each other no matter whether they are all spin ups or they are all spin downs, but all the spins are parallel to each other. That means this dot product will give you a positive sign already, because even if you have both plus 1 and plus 1, you will having a plus 1 as a product, and even if you are having both minus 1 and minus 1, this will always anyway give you a minus and minus cancels out in the product and give you a plus sign. So overall saying is that your SI dot SJ product will be positive always if the system is a ferromagnetic system, so that all the spins are parallel to each other. That means your first term was minus J SI/SJ, and this part I am always anyway saying that this is always be positive. This will always be positive for ferromagnetic systems, which is the general idea of Heisenberg's model. Then to have a minimum energy, that means the minimum value of the Hamiltonian, or in other terms the minimum energy state is your most stable state, you will have to have a minus sign in the whole energy term. So if this part is already positive, then the only thing that can make the Hamiltonian as negative from this term, if you only assume, so then you will have to take the condition that your J is greater than 0. Because other than that, if you took J less than 0, then this minus on the front and this J's negative sign will be cancelling out each other, and you will be having a positive value in the Hamiltonian. That means your energy will not be minimized, or you will be not be having a stable state. So to minimize your energy and have a stable state configuration, you must have your J to be greater than 0. So to minimize, the system's energy, the Hamiltonian has to be negative overall to find the most stable state. And because the Hamiltonian has already a negative sign, and because your SI/SJ is positive, so that means the only thing that can assure the negative sign in the Hamiltonian or the minimization of energy is that to ensure this, you will have to have the condition J greater than 0. So that means our first option was actually true, that for Heisenberg model, exchange interaction integral J is greater than 0. So this is the common for, because we assume that commonly Heisenberg's models are meant for ferromagnetic systems. So the first option was not false, so that is not our answer. And the second option was something about, I think, super exchange interaction, and it was said that for super exchange interaction the J value will be less than 0. Now whether that will be true or not. Now we have not studied in much details about the super exchange interaction, and at this point we do not need to go into greater details. Exchange interaction is enough for us to know in details right now, but I'll just give you a brief idea, like in some few lines, that what is super exchange interaction basically, and how we can conclude that J will be less than 0 for that, because that is also a true option. So your super exchange interaction is not, so it is super exchange because it is different from the normal exchange interaction. And how it happens is that it happens between nearest neighbor, like between neighboring magnetic moments, which are mostly like nearest neighbor, next nearest neighbor cations, and exchange between them happens via the exchange of electrons between via an intermediate anion. Okay, so that is known as exchange center. So what I mean to say is that it's a coupling or interaction between two neighboring, which are more or less in close proximity to each other, neighboring magnetic moments. Now generally it is seen that these neighboring magnetic moments are generally cations, that means positive ions, who are next nearest neighbor to each other. That means the term that is next to the nearest neighbor. Okay, so there is one gap and then the other term, so which are next nearest neighbors. Coupling between the neighboring magnetic moments who are which are cations and next nearest neighbor to each other, and this coupling happens via electronic charge exchange with an intermediate non-magnetic, so this is important, the coupling happens between two magnetic moments, but via which it happens is a intermediate non-magnetic anion or a negative ion. And because this is the via this non-magnetic anion it happens, so this is termed as exchange center for the super exchange interaction. So basically the idea is that this kind of thing is mainly seen also in MNO type of systems. So magnetic manganese moments, you know, they have magnetic moments, so manganese ions will be magnetic, but oxygen will be non-magnetic, so it will be bonding like this, where you have manganese on both sides and in between there is oxygen. So clearly this Mn plus and Mn plus, they are cations, there will be cations and they are next nearest neighbor to each other, because this second Mn is not right beside the first Mn, there is a intermediate atom or ion present which is this oxygen. So this Mn and Mn are next nearest neighbors to each other and they are cations, as I said in the definition, because they have positive charge. You know that Mn plus is a positive ion or cation, and in between there is a O2 minus, which is a oxygen anion because it has a negative ion value, and it is non-magnetic. Oxygen has generally no as such magnetic property in this case, no moment, so it is non-magnetic. And so basically you have your plus 1 cation here and you have your plus 1 cation here, and this minus 2 is your oxygen anion which is non-magnetic. So this is magnetic moment, Mn has magnetic moment, the other Mn has also magnetic moment, but the oxygen in between is non-magnetic, and this Mn and Mn are coupled via the intermediate oxygen atom. How? That is via electron exchange. So if you just want to draw the typical orbital structure here, so this will be like a dz square orbital, where you have a single spin present, like this is unpaired spin, because this is magnetic, so it will have unpaired magnetic moment or spin, so as usual. Yeah, so this is the up spin, and then the other Mn also, this will also be a, so I may not be drawing it properly, but this is, understand, this is a dz square orbital, and here you will be having a down spin, a single spin again, but down spin, because they are the magnetic moments of manganese, and the oxygen will have a p orbital in between. This is the pz orbital, and you have this two spins here. That means there is a spin pair present. It is not uncompensated spin moment, so that is why oxygen is non-magnetic in this case, and this will be like one spin like this and the other spin like this. So via, you can see that manganese magnetic moments are being coupled on next nearest neighbor positions and with a cationic ion form, via the intermediate exchange center, which is the oxygen atom in this case, which has no magnetic moment because the electrons are paired up, not a unpaired moment. And via electron exchange, this kind of a bonding happens, and this is called super exchange interaction, and oxygen in this case is the exchange center. And the magnetic moments of Mn are coupled via the oxygen electron exchange. So this super exchange is mostly, you can see this is not a direct exchange because Mn and Mn are not directly having any exchange interaction with each other, but it is happening via the intermediate exchange center, which is the oxygen atom. So this is kind of an indirect interaction that is happening between the two magnetic moments of Mn. And for now, it is sufficient for you to know that for general exchange interactions, the J value can be positive or negative depending on whether we are talking about ferromagnetic kind of interaction or antiferromagnetic kind of interaction. So in normal or direct exchange interactions, so this indirect interaction is the typical super exchange interactions nature, that it is indirect. Okay, so in direct exchange interaction, generally we have both the options of J greater than 0 if the system is ferromagnetic, so that is what gives us the stable configuration J greater than 0. Or it can also have J less than 0 if the system is antiferromagnetic, so then only this J less than 0 will give you a stable structure, because in that case the spins will be antiparallel to each other like this. So if your SI is plus 1 up spin, then your next nearest neighbor Sj will be minus 1 because that is down spin. So always this Si and Sj product, vector product that we had in the first term of the Hamiltonian will be a minus sign. Okay, because this product will be minus, and there was already a minus sign in the front. So this Si dot Sj Ij. So this minus sign and this product minus sign will be cancelling out each other and make the whole thing plus. Now to have a minimum energy and therefore a negative sign in the Hamiltonian, the only option left is via J. So you have to take a J less than 0 for take the Hamiltonian as negative and the minimum energy state. So this is what we have in direct exchange interaction. And in Heisenberg model, as it is mostly modeled based on ferromagnetic system, that is why the option 1 was correct, that it is based on J greater than 0. But mostly it is sufficient to know for you right now that super exchange interaction mostly prefers antiparallel aligning of the spins, like antiparallel alignment of the magnetic moments, because you can see from the picture here that here the first Mn atom has the spin up state, but the second Mn atom has spin down state. That means this spin and this spin of the two Mn is actually coupled via an intermediate oxygen atom which has net spin 0 because no magnetic moment, it is paired up. Okay, so this is the super exchange interaction happening indirectly between these two, and they have opposite alignment of the spins or the magnetic moments. So that is why you can see this antiparallel alignment only suggests that here J will be less than 0, which is the antiferromagnetic type. So the answer is that for super exchange interaction we will already have J less than 0 in the Heisenberg model. So the second option was also correctly given to us. Now the third option was that whether in indirect exchange interactions the J value actually oscillates with distance. So this is again a true option because mostly, so now the third and the fourth options are kind of connected. So one indirect exchange interaction example I will give you, that is the RKKY interaction. Okay, so this is a very important example of indirect exchange interaction, which is RKKY. RKKY interaction. What is RKKY? RKKY's full form is, it is named after 4 scientists who had proposed and solved this form, introduced this interaction term very first. So this is Ruderman, Kittel, Kasuya and Yoshida. So in short, this is RKKY interaction named after the four scientists behind it. So the interaction idea is that it is basically an interaction between the nuclear magnetic moments, or a coupling between two nucleuses magnetic moments which are like neighboring to each other, via the conduction electrons that is present in between those atoms, or in around those nucleus. Okay, so it is like you have two atoms nucleus here. So let's say nucleus spin I marked by red. So this is one spin, and this is, let's say, another nucleus spin from another atom. Okay, and there are also in the nucleus around there are separate orbits where the electrons are present, conduction electrons are present with a separate spin. So this I am drawing electrons by this white arrow, and the electrons have some random spin alignments. There is no typical alignment in the electrons present. And also in the whole system, in the system of atoms, there are separate atoms present together, many atoms, and the atoms consisting of electrons. So this is basically sitting in a conduction electron sea basically. So around this, in many random orientations, the electrons can be present because they are conduction electrons. Okay, now if you just take the distance between the two nucleuses, this is, let's say, r. So this is the distance. This is your distance between the two nucleuses, interatomic distance you can also say. And so this I mean conduction electron spin, which are random. And by red arrow, I mean nucleus spin. Okay, and r is the distance between them. So it's like that your nuclear magnetic moments are indirectly coupled together via the intermediate conduction electron C. So this is your RKKY interaction. Obviously this is an indirect kind of interaction because this is happening via the conduction electrons, not the direct interaction between the spin moments of the nucleuses. So nuclei, and the nature, if you just want to plot your exchange interaction strength or exchange integral J with the distance between the two atoms or two nucleuses effectively, you will see that this goes somewhat like this. Sorry, let me try it once again. And finally it saturates. So this is like an oscillatory nature of J with distance between the atoms or distance between the two nuclei moments. Okay, so as you increase the distance, firstly you see that J value comes from positive, then it crosses the zero line and goes to negative. So this is positive side, this is the negative side. Then after a point it again comes back to the positive side and goes to the negative side again, and this continues this kind of oscillating behavior, and for a large R maybe it becomes constant. Okay, so from here we see that your exchange interaction changes sign from J greater than 0 to J less than 0 in an oscillatory manner with varying distance between the two nuclei, or it can also be atomic distance between the two atoms, atomic centers. And this oscillation is observed because it is explained that it happens because of the interaction going on between the nuclear moment and the conduction electron. And the oscillation due to interaction of, so first of all, because this is an indirect or via kind of interaction, so first of all the conduction electrons will directly interact with the nuclear moment that is present, and then via that interaction will be interacting with the indirectly with the other nuclear moment. So first of all, the interaction of the direct nuclear moment and the electrons will happen, and that will cause the oscillation in this oscillatory kind of feature in the J value with the distance r. So if you just go to the options that are given to you, you'll see that question number 2, the option number 4 is the only option that is false, because option number 3 also said that indirect exchange interaction leads to oscillatory values in J in Heisenberg model. That I have already showed you that RKKY is itself an indirect kind of exchange interaction, and that gives you an oscillatory value like this up and down kind of thing. Okay, so that is why with distance it will have oscillatory value, and RKKY finally interactions gives J less than 0 in Heisenberg model is not true. This is false, right? That is why this is our answer, because we already showed that RKKY is itself an indirect kind of exchange interaction, which is like option number 3. So with distance it will have oscillatory values, and that is why it will keep on changing sign. So it will keep on, sorry, yeah, so it will keep on changing sign. So there will be no fixed sign that J less than 0 or J greater than 0, but J sign will be changing from positive to negative as we change the distance or R between the two atoms. Now question number 3 is that which of the following is true for a Heisenberg Hamiltonian in 3 dimensions. Okay, so again it concerns about the Heisenberg model and its Hamiltonian. You can see the structure is the same, minus J SI Sj vector product with the Ij in bracket, that means in nearest neighbors, and Ij goes from 1 to etc values because they are different spins. And the options are, one is that adjacent spins are fixed in opposite directions in the ground state for J greater than 0. Now for J greater than 0, you know that it will be like a ferromagnetic kind of interaction. That means all the spins will be in a parallel direction or the same direction to each other. That is the ground state or the most stable state, as I already explained why for the Hamiltonian in this case. But it is said that adjacent spins are fixed in opposite direction, that means anti-parallel, which is not true obviously, because then you will have a antiferromagnetic ground state which will have J less than 0. But for ferromagnetic ground state J greater than 0, you will only have spins which are all aligned in the same direction like this. So this is false. Okay. Second option is that all the spins are aligned in one direction for J greater than 0. Obviously this is the correct answer, because that is why I just said that J greater than 0 means the system is ferromagnetic, and the most stable or the ground state for the minimization of energy will be having all spins are aligned in one direction. So this is true. Third and fourth are also false. Why? We will just read out and guess, read out and understand that first half of the spins are in opposite direction to the other half for J greater than 0. Again J greater than 0 stops the question for you, because this is already a ferromagnetic system. So there will be nothing like some portion in one direction and some portion of spins in other direction. So this is always false. And fourth is none of this ever. This is also false. So this is right. This is done. Answer is option number 2. Then question number 4 is also again a mathematically solvable problem. So we'll be solving this. First read out the question that there is a linear chain of 3 half spins. That means this is a 3 spin systems. You have S1, S2 and S3, and with periodic boundary conditions. That means even if this is a 3-spin system, but this, because of periodic boundary conditions, there will be like a closed system. So this is if S1, this is let's say S2, then this is S3. So you will be having S1, S2, S3 in a closed compact periodic boundary condition manner. This will be not like a 1D chain which are discrete and open on both ends. So this is the other option that it could have, but this is not the case since it is mentioned in the question that it is having periodic boundary condition. This is not true. This is the true structure. Now with both the spin-spin interaction and a Zeeman term with a magnetic field in the z direction, the Hamiltonian of the system is given by, so the first term is known from the spin-spin interaction term, nearest neighbor, and the second term is minus gs nu b by h cut sum over j sjz. So this is your Zeeman term that is explained over here. This is Zeeman term because this is dependent on the external field b, and this gs is the Landau G factor, nu b is the Bohr magnetron, you know, and Sj is Sjz is sum of all the z components of spins. Z component is taken because when you take a dot product with the field is already in the z direction, so the spins will be always taking the z direction in the second term. Now with this Hamiltonian, where the symbols have their usual meaning, you have this spins written in another form, which is like somewhat like creation and annihilation operators are written like that. So you have S plus minus j defined like S plus j is equal to sjx plus ij sjy, and sj minus is defined as sjx minus isjy. Now the interaction between the jth and the lth spin sj dot sl can be written as, where h cut equal to 1, you have to know the answer. So let us take a blank page and solve. This is question number 4, and let me just first write down what was your relation given, that sj plus minus equal to, so basically it means let's take one by one. Sj plus equal to sjx plus I sjy, and your sj minus equal to sjx minus I sjy. Okay. So you can separately calculate what is sjx in terms of sj plus and sj minus. So this is simple, you just have to add it. So the second term will be cancelled out, only 2 times sjx will be there. So this 2 will be coming as a division of 2 here on the other side. So this is sj plus sj minus by 2. Similarly, you can take out what is your sjy value in terms of sj plus and sj minus. So if you just minus of these two, subtract these two terms, so this sjx and sjx will be cancelling out with each other with a minus sign, but this isjy with this minus of minus isjy, you will be having a 2i sjy. So basically this thing, you will have a 2i in the denominator. So you will have sj plus minus sj minus by 2i, right? And the Hamiltonian was written as your h equal to j h cut minus 2, jl are nearest neighbors, so sj vector dot sl vector minus gs mu b h cut j sjz, z component. So this is the spin-spin interaction term, and this is your Zeeman term coming from the external field B. Is along z cap, so this is B times z cap. Now we have to calculate what is sj dot sj vector dot sl vector. So this is, we have to calculate what. This is basically a dot product between two separate spins sj and sl. So how to first of all like simplify your dot product. So you have to just product it term by term. So this is sjx slx plus sjy sly plus sjz slz. Now you know that what is the sx component taken out from here, sj plus sj minus by 2, and because it is a j component, so this is like j sj plus sj minus by 2. Similarly, SLX will be, instead of J, will be having this time component, this time the index is L, otherwise everything is same. So this is SL plus SL minus by 2, plus the second term is Y. So you know the Y is formed that this is simply Sj plus minus Sj minus divided by 2I. And similarly for L, everything will be same, just the J index will be changed into L index. So this is SL plus minus SL minus by 2I. And your third term will be remained as it is, because this is the Z component, there is no decomposition for this form. This is already in a simplified manner, only the Z component. So now if you just multiply these terms together, so this is 1 by 4 Sj plus SL plus, just product it term by term, so this is Sj plus SL minus Sj minus SL plus Sj minus SL minus. Okay, then plus 1 by 4, this is 2I into 2I is 4I square, and I square giving you a minus sign, so this is minus 1 by 4. Then you have Sj plus SL plus minus Sj plus SL minus Sj minus SL plus minus a plus Sj minus SL minus, plus the last term is just Sjz SL Z. Now you take this 4 common and you have, just write all of them together. Be careful about the sign. Sj plus SL minus Sj minus SL plus Sj minus SL minus. And then the second terms has all the signs as minus. So minus Sj plus SL plus minus plus Sj plus SL minus again plus Sj minus SL plus, and then again last is minus Sj minus SL minus plus Sjz SL Z. Okay, so now just look very carefully that which of the terms are cancelling out already. So like which are opposite in sign but equal. Okay, so Sj plus and SL minus, does it have any common? So sorry, Sj plus and SL plus, both are plus. So this is the thing, Sj plus and SL plus, this thing has equal and opposite signs to each other, so they cancel out already. And then Sj minus SL minus, is there any term like that? We find it out that no, there is no such term, I think. Oh no, oh sorry, there is another term like that, so this is cancelling out again. So whatever we are left with is that half into, now this Sj plus SL minus is present 2 times, so we'll just have to do a twice into 2, and also this Sj minus SL plus is also twice, so just take the 2 factor outside and remains Sj plus SL minus Sj minus SL plus, and also the remaining term is Sjz SL Z. So you have Sj plus SL minus Sj minus SL plus by 2 plus Sjz SL Z. So this is your final answer. Let us match whether it matches with our answer. Sj plus SL minus and Sj minus SL plus. Let us go back. Option number Sj plus SL minus and Sj minus SL plus by 2 plus Sjz SLz. So this is option number 3. This we have calculated that this is the answer that is coming for us as well. Okay. So this completes the 4th question. And the 5th question, okay, so this is again a conceptual question. So maybe I'll just first skip to question number 6, and then after solving that, this is the mathematical question. So after solving question number 6, I'll be coming back later to the question number 5. So question number 6 is that the Hamiltonian of two interacting particles, one has spin 1 and the other has spin half, is given by H equal to alpha S1 vector dot S2 vector. So S1 and S2 denotes the spin operators for first and the second particle. Alpha is a positive constant, then the largest eigenvalue of this Hamiltonian is what? So basically your S1 is for particle 1 spin operator, and here the spin value, like this mod S1 equal to 1. S2 is the spin operator for the second particle, and the mod spin value in this case is half. And they can interact with each other, that is why this is the interaction Hamiltonian, and here your alpha is greater than 0. Then what is the largest eigenvalue of this Hamiltonian? So let us go back. This is question number 6. H equal to alpha S1 vector dot S2 vector. You know that the total spin of this system is just a vector summation of the individual spins, right? So total S vector equal to S1 vector plus S2 vector. That means your S whole mod squared magnitude square equal to S1 whole mod square plus S2 whole mod squared plus 2 S1 vector dot S2 vector dot product. So if we just take out what is the S1 vector dot S2 vector, we will be having mod S squared minus mod S1 squared minus mod S2 squared divided by 2. So this is the thing that you have to use in the expression of the Hamiltonian to get the eigenvalues. So your Hamiltonian is alpha by 2 S1 by alpha S1 dot S2, right? So just replace this S1 dot S2 in the Hamiltonian. So this is alpha by 2 S squared minus S1 squared minus S2 squared. Now you know that if S vector equal to S1 plus S2 vector, then the eigenvalues, the S values that are possible for the from the combination of S1 S2 values are basically, so you know that your S1 is equal to 1 and S2 equal to half. So S can take values like either modulus of subtraction of S1 and S2, or the other value can be just direct sum of S1 and S2. So this will be like 1 minus half modulus, then 1 plus half. So this is like half and 3 by 2. So the modulus of this total spin mod S can take two type of values, either half or 3 by 2. So because it is asked in the question that you have to take you have to calculate the largest eigenvalue of the Hamiltonian, that means the maximum value of the total spin value will have to be used. Otherwise the H will not be the most, like the highest value, or the most the largest eigenvalue of the Hamiltonian will not get. So that is to ensure that we just choose the S equal to 3 by 2 value, because that is larger than half, and that will give us a larger value of the Hamiltonian. So we choose here mod S equal to 3 by 2 as it is the largest among the other eigenvalues, and this S1 is already fixed at 1 and S2 is already fixed at half. So now if the eigenvalue has to be calculated for S1 mod squared, so I think there is some confusion that will be happening in this case if you just denote it by S1 mod, S2 mod, etc. Because there actually what is that they are actually the Z components eigenvalue. That means this is, let's say, small s, which is 3 by 2. Then small s1 is half and small s2 equal to, small s1 is 1, small s2 equal to half. So these are like the eigen value for the Z component of the spin. So for S1 whole mod square, you will have to take, because you know that this S vector, if this is an operator, if this is acting on a state psi, then it will have S into S plus 1 h cut square psi. So that is how you get mod S square equal to S into S plus 1 each cut square, which is 3 by 2, 3 by 2 plus 1 each cut square. So this is 3 by 2 into 5 by 2, 15, 4 each cut square. Similarly for S1 squared whole mod is equal to S1 plus 1 each cut square. This is 1 into 1 plus 1 each cut square. This is equal to 2 each cut square. And S2 whole square equal to S2 plus 1 each cut square equal to half plus 1 each cut square. So this is 3 by 4 each cut square. So the total value will be like H equal to alpha by 2 S square minus S1 square minus S2 square. So this is alpha by 2. S square is 15 by 4 each cut square minus S1 mod square is 2 each cut square minus S2 mod square is 3 by 4 each cut square. So you take out each cut square. This is 4, this is 15, 8, 3. This is alpha each cut square by 2, 4 by 4. So this is half alpha each cut square. So the answer is half alpha each cut square. So let us check whether we got the answer or not. Yes, so the option is correct, that you have also got so this is your answer. So this answer number 3 is also option number 3 is given for answer question number 6. And then mostly what we are left with is the not analytical problem, but these are mostly like explanatory question or conceptual problems. Okay, so let's continue. So I was discussing the problem number 6 to you first, and I left the question number 5 for later. So let us try question number 5 then. So it is saying that the quantum of spin wave in ferromagnets is called magnons. That you know that magnons are basically the quantized version of spin wave, and it is seen in ferromagnets. Which of the following is true for magnons in a ferromagnet? So you have to choose the true option. Now option number 1 is that magnons are fermions and hence follow the Fermi-Dirac statistics. So this is absolutely not true, because you know that fermions are bosons, bosonic particles, just like you know that lattice has phonons. Phonons are vibrational modes in lattice which are quantized, right? So similar to that, magnons are also the quantized version of the spin wave in ferromagnet. So they are all bosonic particles, and hence they do not follow Fermi-Dirac statistics, but they follow the Bose-Einstein statistics. So the first option is not true. Second option is that at long wavelength limit the energy is proportional to k square. Now this is the true option. I will show you the derivation why. And as the option number 2 is correct, then option number 3, which says that at long wavelength the energy is proportional to k, that is incorrect obviously. And option number 4 is that magnets are classical distinguishable particles and hence follow the Maxwell-Boltzmann statistics. That is also not true, because in discussing option number 1 only we said that they are bosonic particles. That means they are quantum particles. They are indistinguishable from each other. They are not like classical or distinguishable. And as a result, they do not follow the Maxwell-Boltzmann statistics. They follow the neither do they follow the Maxwell-Boltzmann nor the Fermi-Dirac, but they follow the Bose-Einstein statistics. So yeah, so magnets are bosonic particles, they are quantum particles, and they are indistinguishable from each other, and that's why they follow bosonic. So they follow the Bose-Einstein or BE statistics. So option number 1 is incorrect, option number 4 is incorrect. Now between 2 and 3 we have to choose why 2 is the correct answer. So that for that we have to derive at long wavelength limit, that means at lambda tends to infinity, what is the energy dispersion relation, that means what is the energy relation with the wave vector k for the magnets. So this we have to calculate, then we will know that why it is proportional to k square and not k. Okay, so let us go to the derivation of that. So question number 5, right? Magnons energy dispersion relation. Okay, so we know that the Hamiltonian, if this is a Heisenberg model, then the Hamiltonian, sorry, so the Hamiltonian for a Heisenberg model will be like this: minus j I j si dot si plus 1. So here instead of taking ij, where we take si dot sj and ij at the nearest neighbor, instead of taking that, we just consider that it is like a one-dimensional chain model to simplify the whole thing. So if this is a one-dimensional chain model, then the nearest neighbor of the ith spin will be obviously I plus 1th spin, because this is in one dimension. Or if the spin is sitting in the middle portion of the chain, then it can also be the I minus 1th spin. And based on that, we'll be having a sum over I. So this is basically equivalent to this form, where this is si dot sj, where ij is in the nearest neighbor format. Okay, but because we have simplified the problem to a one-dimensional chain, then we can take what is the j value, that will be either I plus 1 or I minus 1, and based on that the summation will be the same. Okay, now we know that in quantum mechanics, if there is an operator which is like x cap, and you have the Hamiltonian and h cap, so their commutator bracket will be having a relation like this. This I will not be derivating explicitly, you can check it out from any quantum mechanics textbook, that this comes as I d x dt, time derivative. Okay, so something like that. If you take a also a like outside the commutator bracket, if you take a this average or expectation value, then you will be having expectation value of x and then its time derivative on the other side. So this is your formula that you need to know when we solve or derive this. Now here to solve the energy dispersion of magnets, we use a semi-classical treatment. This is also discussed in the lecture itself, so you can check it out from there. In semi-classical treatment, we basically what we do is that we consider that each spin side, the spins are behaving like a classical vector which has three particular components x, y and z, and instead of the spins in normal case, if the field is along z direction, so the spins in the ferromagnet will be actually explicitly aligned all parallel to the z direction. But in this case, we consider that the spins are very like slightly deviated, each of the spin are slightly deviated somewhat from the z axis orientation, so that it can have a non-zero value even in the x and y component, which are very small value obviously, but they are not completely zero. So like say in normal ferromagnet, if your z direction is a field direction, then your spin is always like this, okay, explicitly along z cap. But for magnets, we consider a spin wave, right? So to consider the spin wave, we take that if this is your z direction, okay, so this is your z direction and your spin is not aligned along this but slightly deviated from here, okay, so this is, let's say, your spin. And similarly, if you just go along this line, you can continue, like the next case you will be like more closer, so it will be like vector. Now the spin has shifted even this point, and the next point it will be shifted towards the other side like this, okay. and then here. So like this. So these things will happen. So you can check it out from the lecture itself that the spin wave concept actually allows us this thing, and the separation between each of the spins is a lattice constant, which is a lattice constant. And you can like call it a spin wave because if you just take the arrow point where it touches the line, it will be forming a wave like shape. So it is like, if you check from a top view these spins orientations, if you check from a top view, then you'll be having something like this, then this, this the kind of thing will be continued. So I am not drawing it properly maybe, but you can check the exact schematic from the NPTEL textbook or even in the lecture materials. Okay, so this is basically your one-dimensional spin wave from which we define the quantized version or magnons, and for magnons we are starting to calculate the energy dispersion. Now the approximation was that in general case your spin is actually parallel to the z-axis. So then your sz is your total spin value s, and the sx and sy components will be 0 because there will be no component along x and y, right? But in this case, if the spins are like slightly like tilted from the z direction, then your sx and sy are non-zero, but they have a value which are much smaller than the total spin value s. And on the other hand, your sz is not exactly equal to s like before, but its value is very much closer to s, like it is actually contributing to the maximum spin contribution is from coming from the z component. So it is almost equal to s, you can say, but s and sx and sy has a very little finite value which is non-zero and which is much smaller than s. So this is the assumptions that we will be using. Okay, so let's say these are our assumptions for the semi-classical treatment of the Magnus energy dispersion solution. Now because you know the Hamiltonian format, so Hamiltonian is minus j sum over I si dot si plus 1 nearest neighbor, and then you know how to calculate each of the, like we want to calculate the derivative of the spin for the x, y and z component with respect to time for each of the components. So we just have to calculate I dsix dt. So it will be nothing but the commutator bracket of six comma h, right? So it is like, let us calculate it elaborately. So h is, just put the value minus j sum over I si dot si plus 1. So minus j, it is a constant, so it comes outside, so minus j, then second bracket starts. Now carefully choose the commutator bracket together. So first term is fixed, so it is six, and the second term can be, now this is useful that it can be, you can take the dot product term by term, like this is si x si plus 1x plus si y si plus 1y plus si z si plus 1z. Or because I said that in a one-dimensional chain, the nearest neighbors are on both sides, it can be present, like si can also be there with si minus 1, right? Because that is the other side's nearest neighbor. So there can also be terms like si minus 1x, si x, then si minus 1y, si y, plus then the z component. Okay, so that I am not writing, just assume that it is here. So accordingly, we take the commutator bracket. So first term is six, si. So just let me write it, so it will be probably convenient. Then we won't repeat it in the second line and just go on with separate commutator brackets. So the third term will be the z component, which is si z, si plus 1 z, and here the third term will be si minus z, si z. So just take term by term because it is a summation. So you just have two terms for this from the summation, like one is because you have to take SI only. Other than that, if you take other spin, then this will be giving you a zero value from the commutator bracket relation, because I have already told you that for the commutator bracket relation to be valid and non-zero, firstly you have to have same spin. Like if the left side is SI, then the right side should also have SI part. So we ignore the other terms from the summation and only take those terms which have SI present somewhat. So SI can only be present with two sides of nearest neighbors. One is I plus 1 and the other is I minus 1. So that is how we have like decomposed this product term, and we can just take term by term right now. So the first term is SIX, SI plus 1x. So just take first SIX commutator bracket and SI plus 1x remains. Then you have SI plus 1x, then leave the SIX behind, okay, because I have taken this term inside the commutator. Then similarly you have for y also you will continue. So SIY, SIX, SIY, SI plus y plus SIX, SI plus 1y, SIY. Okay. Now just go alongside that, whatever terms are cancelling out, let's just cancel that out properly at the first only. First of all, this I and I plus 1 are separate spins. So firstly they will be 0, and this is I and I plus 1, it will be 0. So these two terms are 0. This is both I and this is also I and I. So these are not in that category, but SIX and SIX both are x components, so again it will be 0, right? But this is x and y, so it has some finite value. We'll leave that for now. Now the third, like with z, we have to continue. So this is SIX, SIZ, SI plus 1z plus SIX, SI plus 1z, SIZ. So then I and I plus 1 again makes it 0, and x and z with I both will be having a finite value. We'll take that later. So this part is with I plus 1 everything is covered. Then we move on with minus 1 terms. So it is giving us SIX, then SI minus 1x, SIX. This will be 0 because I and I minus 1 are separate spins. Then SIX, SIX, SI minus 1x. This will both are I, but both are from x component, so it will again be 0. Plus then take the y term, SIX, SI minus y, 1y. Both are I and I minus 1, so 0. And SIX, SIY, SI minus 1y. So this is non-zero because both are I and both are from different components. Then for z you have SIX, SI minus 1z. This will be 0 straight cut because I and I minus 1 are different. And the last term will be SIX, SIZ. This is non-zero because I and both are x and z. This is that. Now the only remaining terms will have the commutator bracket relation value to be used. So this term is SIX and SIY. So in a clockwise manner it will be giving you I. Now let us leave out the, I think the each cut, consider it as 1. So each cut equal to 1 considered. So it is just I, SIZ, and the remaining term was I plus 1y. Plus this SIX, SIZ is basically x and z is giving you in a counterclockwise manner. So it is minus I, SIY, SI plus 1z. Then you have this term where you have x and y in clockwise manner. So this is I, SIY, SI minus 1y. And the last term is x and z again in counterclockwise manner. So it is minus I, SIY, SI minus 1z. So you have whatever terms we are left with, let us collect that. So you have SIZ, SI plus 1y. So your dSIX dt equal to, take the minus sign inside, so this j, then your sorry, this I, and there was also the I will be taken as common, so I and I cancels out. So this is just j, and minus sign taken inside, that makes it si y, si plus 1 z. I think I made a mistake somewhere, so this third term will be, just let me check 1 second. So that is why these are very crucial, otherwise there is a high chance to make mistakes. um, um, yz zy, and okay, yz terms will be present, so this is fine, that si y, si plus 1 z, then minus this term si z, si plus 1 y. So this will be taken together, because this has become now plus and this has become minus, absorbing the minus sign outside the bracket, and then plus, this has now become plus, so this is si y, si minus 1 z, then this term has become minus, so minus si y, si minus 1 z. So here I have probably made the mistake that just 1 second, let us go term by term again. I have probably mixed up some y and z component again. So si z, right? So si x, si y, si minus 1 y, xy making it z, and then okay, alright, so the mistake is basically I had x and y, so it will be like z. That is what I was searching for. So it will be z, because you see that this is si x and si y commutator, so this will be giving you a si z. So this will have a minus sign now, absorbing that minus sign outside. So this is si z, si minus 1 y. So this is your final result. So you continue that this is your dsix dt equal to j common si y. Now you just put the values for each of the spins based on the assumption that we had earlier, that the spin is slightly tilted from z orientation. So just that the sz component is nearly equal to the total spin s, but sx and sy are very small, much smaller than s. So you do not put the x and y component values, but we directly put the z component values nearly equal to, so there will be a nearly equal to sign. Okay, so because this is not exactly s, this is just nearly s, so we put the z components as s. So this is si y into s minus s into si plus 1 y plus si y into s, again minus s si minus 1 y. So just use a separate bracket so that you don't confuse it with the commutator bracket again. So all the z components, irrespective of if it is I plus 1 or I minus 1 at spin, but all the z component value are nearly equal to s. Now simplifying it further, you have dsix dt is nearly equal to j. So there will be s will be taken common, okay, and then you have 2 si y, right? So this is 2 si y minus a single si plus 1 y minus another single si minus 1 y. Okay, so this is one thing. This is, let's say we mark it as equation number 1. Similarly, you can follow up the same calculation by yourself. This is just similar to the thing we did for I x component. So this will be like, you will be having I dsi dt equal to commutator bracket of si y comma minus j sum over I si dot si plus 1. Again you break it out into x, y and z components in a product. and then each of the terms you have to take for both I plus 1 and I minus 1 and decompose similarly just we had done here. So you can take out each of the commutator brackets separately, cancel out the terms which are relevant to cancel out, and then finally I'll give you the solution. I'll give you the final form. After simplifying the whole thing, you will be having a similar thing. So finally you will be again putting the Si or Si minus 1 or Si plus 1 Z component as nearly S. So this is nearly equal to, now there will be a minus sign extra, minus Js, and it will be like 2 Six this time minus Si minus 1x minus Si plus 1x. So this will be your equation number 2. And similar thing if you can continue for Z component also, d Si Z dt equal to Si Z comma J I Si plus 1 vector. If you take the commutator bracket, solve it term by term, and finally put the Si Z value nearly equal to S, you will be getting a almost 0 value. So this will be nearly equal to 0 because all the terms will be cancelled out. Okay, so you will be having d Si Z by dt to be 0. So this is your equation number 3. Now once you have got these equations, so from 1 and 2 you will see that if you try to solve, you will assume traveling wave solutions. That means for standing wave you do not have a time dependence. In traveling wave solution, with a plane wave solution like e to the power I kx sort of a form, you have an additional time dependent form like e to the power of I omega t or minus I omega t. So you will be using that, right? Because there is a time derivative, so obviously there will be a time dependence present in the wave function solution. So based on that, we choose our two solutions as Six to be chosen as some component u times e to the power of I kx. Instead of x we put IA minus omega t is for the time dependence part. So this remember that this I in the front of the bracket is I equal to root over of minus 1, complex I. But here this I is nothing but your, like, to map out the whole distance of x. So like you have the lattice constant A, so if you have I number of spaces between the number of spins, so each of them are A distance. So you have, like, here you have say 3A, right? So basically if you are going from here to here for 4 spins, you are taking up 3 spaces in between, which is equivalent to 3A. Similarly for I plus 1 spins if you take, so you have I spaces in between and the total distance is IA. So the x is here replaced by IA, and this I is basically an index. This is not the complex, this is the index I. Okay, right, and u is just the like amplitude part sort of for the wave. And similarly SIY is chosen as V is the amplitude part, and then e to the power of I KIA minus omega t. Again the front I is root over of minus 1 and the second I is just the index. So just don't mix them up or confuse. So now using these solutions, you put them in 1 and 2 equations. You will get first 1, use 1, so d Six dt, you put it here. Okay, so use the solutions for the components in each of the terms. So first of all, d Six dt, the derivative you take with respect to time, it will be having a minus I omega to the front. This is minus u I omega, where I is root over of minus 1, and then e to the power of this whole thing. So for simplicity's sake, because both of them are I k minus omega t, so just to avoid much confusion, we assume that I kia minus omega t, we for now we take as some p. Okay, later on we'll put the value. So just take it as the power of p, not p, this is ip because this is the complex I, right? So for now, whatever things I continue from now on, as long as I am using this p term to absorb the whole index I inside. So right now all the terms I am writing I in are meaning the complex root over of minus 1 I. Okay. Now this thing will be coming up. So this is minus I u omega e to the power of I p. And now if you put the values on the right hand side, so this is js, 2siy, so you have to use the values of siy on these things. So you will have nearly equal to js bracket 2siy means you put this value, so 2 v I to the power of I, this is p as I already said, then 2 si. Now for si minus 1 x or y, okay, let's say si minus 1 y if you have to calculate, this is the index I, remember, because it is with the spin. So you have to replace this k ia as ki minus 1a minus omega t, right? So then you just separate the two terms. So you take out e to the power I k ia minus omega t as it is, and the extra term is that e to the power of minus ka with the I sign, so it comes out, so e to the power of minus ik, you take that out. So this is your earlier term and this is your extra term that is coming because the index has been changed to I minus 1. Similarly, for any, even for e to the power I minus 1 x also, you will be having u. Just replace the index I as I minus 1, you will be having e to the power of I k minus omega t and e to the power of minus ik, right? So this is same as siy e to the power of minus k, and this is same as six e to the power of minus ik. Similarly, if you have to choose si plus 1 y, then just replace the index I by I plus 1, like here it will be I plus 1. So instead of ik minus ik, you will be having an extra e to the power of plus ik term, which is like v e to the power of this whole third term as e to the power of ip, and then e to the power of plus ik, which is like si y e to the power of ik. And similarly for si plus 1x also, we will be having a six e to the power of plus ik. So this is the thing. For I plus 1 index, the thing is extra factor is I e to the power of plus ik, and for I minus 1, it is the e to the power of minus ik. So the first term has just simply 2 si y. So it is just 2 si y, you use the value v e to the power of ip. P is the whole kia minus omega t term. Okay, so this is just 2 times this thing minus, what was it, si plus 1 y, right? So I just told you that si plus 1 y will be simply si y, that means your v e to the power of ip and then extra ik term, and the third term is si minus 1 y, so the term will be, I have already calculated, so this is v e to the power of ip e to the power of minus ik now. Okay, so just right, so you can just take out v e to the power of ip from each of the terms common. This is 2 minus e to the power of ik, take the minus common, e to the power of minus ik. So this is js v e to the power of ip 2 minus, and now you know that e to the power of ix plus e to the power of minus ix is nothing but 2 cos x. That means 2 cos k. So you just take out 2 j v s e to the power of ip 1 minus cos k. Now again from trigonometric idea, you know that 1 minus cos x is nothing but 2 sin x squared by 2, right? So here your x is k, so this is 2 jsp e to the power of ip 2 sin sorry, I think 2 sin square x by 2 was the thing, so I just mixed up it again. Sorry, so this is not in the argument, this will be sin squared, so this is sin squared k by 2. So this is making it 4 jsp e to the power of ip sin squared Ka by 2. Now on the left hand side from the derivative you had already got minus u I omega e to the power of ip. So the left hand side is minus u I omega e to the power of ip. So this ip and ip both sides common, cancels out. So the thing that we are left with is minus, let's take it to the same side, I think that will be good. So just 2 times and then yeah, so this is like 4 JSV sine squared, sorry 4 JA sine squared Ka by 2 into V plus take this to the other hand, so this is plus I omega times u equal to 0. So this is your equation number 4 we have identified. And similarly from equation number 2, if you just use the ds I by dt, so then you will have, so you'll be using this equation and just substitute the travelling wave solution that we have chosen for SIY and simplify as we have done for SIX from both sides. So then we'll be seeing that we'll get a value similar to this. I'll be just writing it out. So if you just use this whole expression and put the values on both ends, you'll be ending up with minus I omega v equal to minus 2 JSU 1 minus cos k, which is nothing but, so remember this is v and this is your u. So you have take the v to the other side, so plus I omega times v, this is minus, so 1 minus cos k, again 2 sine squared k by 2, so this is 2 and 2 4 js sine squared Ka by 2 multiplied by u equal to 0. So this is your equation number 5. So from 4 and 5, if you want to solve what is the value of u and v, you just have to present it like a matrix, right? So just organizing it in a matrix form, first we take the u component, so this is I omega first, so I omega, and then the component with v is 4js sine square k by 2, this is 4js, and then again, so this is like u and v, this is a matrix equation we are writing to solve it. And then again for u, you have this minus 4js sine squared Ka by 2, and here with v you have plus I omega. So to solve this, you know the determinant of the matrix has to be 0. That means I omega 4js sine squared k by 2 minus 4js sine squared k by 2 I omega, determinant of whole thing is 0. Then just solve the determinant. This is I squared omega squared, which is minus omega squared because I square is minus 1. Then minus and this minus making it plus. So this is 16 j square a squared sine to the power of 4 Ka by 2 equal to 0. So your omega square, take it to the other side, is this thing. So omega is just square root of that, that is 4 js sine squared K by 2. Okay. So now this is the dispersion relation because you know that E equal to h card omega. So if you have omega as a function of k already, because on the right hand side you have k the wave vector and the left hand side omega, you have already got the dispersion relation. Okay. What is left is that because E is proportional to omega, so whatever omega's relation with k will be followed for E also. Now we have to take the large wavelength limit, that means lambda tending to infinity. Because k equal to 2 pi by lambda, it also means that your k is very small or k tending to 0. So you know the idea that if sin x is nearly equal to x for x tending to 0, That means here if k is very small, so ka by 2 is also very small. That means sine square ka by 2 will be nothing but ka by 2 whole squared. So this omega equal to 4j is, it is nearly equal to, this is ka by 2 whole square, which is 4js k squared a squared by 4. 4 and 4 cancels out. So omega as a function of k is just nearly equal to js a squared k squared. So this is the solution for the dispersion relation for large wavelength limit or small value of k. That means you get that your energy is proportional to k square and not k, which is our option number 2 that we have correctly chosen, that this is the correct option. So let us go back. Yes, so this is the correct option, that 2 long wavelength limit the energy is proportional to k square. That is what we got from the dispersion relation. Now for question number 7, says, it is a short kind of question. So it says that if a diamagnetic sample contains a ferromagnetic contamination, there will be a temperature dependent contribution to the total magnetic susceptibility. So what will be then the total susceptibility given by? Now you know that for diamagnetic sample, the diamagnetic susceptibility is completely temperature independent. So it is a constant or temperature independent value, and it is negative in susceptibility value because it is diamagnetic. So if it was a pure diamagnetic sample, then chi will be simple chi dia, which has no dependence on T. But because this sample contains some ferromagnetic contamination, and you know that for ferromagnetic samples the chi goes like C by T minus Tc, where C is a Curie constant, Tc is a transition temperature or Curie temperature. And similarly for AFM or antiferromagnetic systems, you know that the chi goes like C by T plus Tc, where C is the Curie constant and Tc is the Curie temperature, which is negative in this case. So obviously when you have a ferromagnetic impurity present, from that impurity component you will be having some temperature dependence in the susceptibility, which was otherwise absent in the pure diamagnetic sample. So the net susceptibility will be just a summation over both components. One is a diamagnetic part and the other is a ferromagnetic like contamination part, chi dia plus chi FM, which is similar, same as chi dia, which is temperature independent and negative, plus the ferromagnetic susceptibility, which is positive and temperature dependent, which is C by T minus Tc. So your option number 3 is the correct option. This was easy. Now question number 8 is about the Landau's theory of ferromagnetic phase transition. Now we know that the magnetization M is small near the Curie temperature Tc, therefore we can express the free energy as a power series in M. So this power series is given. Okay, Fm equal to some power series of M is given, where A1, A2, A3, A4 up to 4th order is present. Higher order terms are neglected because they have very negligible contribution, and the parameters Ai might have may depend only on temperature. So these parameters are not constant, either they are constant or they are dependent on temperature, not any other parameter. So you have to calculate the equilibrium values of M. So apart from knowing the Landau's theory, so you have to have an idea of Landau's theory and also the idea of how to equilibrate a system if you are given the free energy for the system. So the free energy concept is very simple, that for stable state you know that the energy has to be minimum, right? So for minimum energy we often calculate the derivative of the free energy with respect to the variable to be 0, and after that we calculate the variables value, and that becomes our equilibrium values from the derivative. So this is question number 8, which is about Landau's theory, and you are given the free energy for the system, which is expanded in like a series form about the transition temperature Tc, which is like A1m plus A2m squared plus A3 cube plus A4m4. Now this is very important, that whether you choose your M to be positive or you choose your M to be negative, means spin are of all up spin or down spin, the free energy has to be same. Because very simple, that the stable state, which is the ground state, for the ferromagnet will always have all parallel spins. That means either all of the spins are up, that means M is positive, or all the spins are down or M is negative. But irrespective of that, you will have the similar free energy minima because both are equilibrium states, right? So that is why you have to set this condition that whether your m is plus m or minus m, your free energy will be same for the minimum or equilibrium position. Now this condition makes us take the fm to be an even function in m, because other than that the two things will not be equal, because these odd terms which are m and m cube, when you take or set m to minus m, this will be having a minus sign, making the whole fm different from the actual fm. So to satisfy this condition, we must take these a1 and a3 to be 0. You can just directly put it and also see that fm is simply this whole thing, right? I am not repeating it again, I am just take it from here. And f minus m is just minus a1m plus a2m square, because minus m square is plus m square. And a3, this is m cube, this is odd function, so this is minus a3 m cube, plus last is again even, so this is plus m to the power 4. Now between these two terms of the two parts of the equal sign, so this part, sorry, this is not be cancelled out, so this part and this part cancels out, and this part and this part cancels out, because they are of the same sign and they are on the opposite sides of the equal sign. So the remaining terms are just 2a1m plus 2a3m cube equal to 0. That means if you take common, so this is 2m a1 plus a3 m square equal to 0. Now your m cannot be 0 because you are taking a spontaneous magnetization in this case. So the only option is that a1 equal to 1 second. So now because your m is not 0, so the only option left to make like this also is not valid, because this is not a valid condition. This will not have such a dependence. Then the only condition left for you to take is that you have to set both a1 equal to 0 and a3 equal to 0. But because I have already said that you have to choose your free energy as an even function of the magnetization, otherwise you will not have the same free energy condition for both positive spin conditions and negative spin or negative magnetization conditions. So after that we are only left with the modified free energy with this condition satisfied is just the even terms a2m square plus a4 into the power 4. Now you have to take the free energy minimum or the equilibrium point, so you have to take a derivative df dm equal to 0, and from there whatever m values you get at roots will be your equilibrium points. So df dm is simply 2a2m plus 4a4m cube equal to 0. This is just a2m equal to minus 2a4, just take it like this, that this is your 2m common, a2 plus 2a4 m squared equal to 0. And because m cannot be 0, so the only option is that your a2 has to be set equal to minus 2a4 m squared, or m equal to a2 by 2a4 minus square root plus minus. Now this will not be a complex number, because inside the square root this minus sign will be compensated by the signs of a2 or a4 whatever, but this is your like the equilibrium value of m. Now you will see a slight mismatch with this answer and the given answer in the option, because there is a missing 2 factor. If you go back, there is a, let's say, question number 8. So if you go back, you will see that the option 1 is the correct option given, which is minus a2 by a4 to the power half. Everything else is same, just a 2 factor is missing, which is present in our result. That is because this is a mistake, I think, because in some expressions people take some constant factors with this a1, a2, a3 factors to just make the final form make the final form to look more compact or simplified. In that case, sometimes people also choose this some like say 1 by 4 factor with the a4 or 1 by 3 factor with the a3, so that when the derivative is taken, those extra factors that are coming automatically cancels out. So if you take it like that, so that for that form we'll be having no 2 factor here, but actually there's a 2 factor missing if we base our solution on this free energy expression. Other than that, you can just choose based on the fact that a2 divided by a4 is there. All the other options are not close enough, so we choose the option number 1 as the correct option. Now we are only left with 2 questions, 9 and 10. 9 is about what is false, you have to choose. So RKKY interaction you have been given. RKKY interaction is an indirect itinerant exchange interaction between magnetic moments mediated by conduction electrons. As I had already discussed this thing to you in a previous question, so you know that RKKY is indeed an indirect interaction, and it happens between the nuclear magnetic moments via conduction electrons. So this is true option, so this is not false. Then second is that RKKY interaction is long range. This is also true because RKKY has to be long range because the magnetic moments can be separated far away and they are only coupling mediated via the conduction electron. So they have long range interaction range. That is why this is true. And the third is that RKKY interaction is relevant in rare earth metals. This is also seen that mostly in rare earth compounds which has D or F electron cells, they have this kind of a RKKY interaction behavior present because in those elements the nuclear magnetic moment is strongly present and which is localized, and there are like one of the cells have the conduction electrons which is the itinerant electrons, and they actually contribute in the indirect exchange interaction between the magnetic moments. So this is why this is also true. And the fourth is that RKKY is a direct exchange interaction. This is obviously false. So this is actually your right answer 4 because RKKY is an indirect exchange interaction. Okay. And the question number 10 is that which of the following statements is not true for ferromagnets? So first is the characteristic feature of ferromagnet is a spontaneous magnetization, true, which is due to alignment of magnetic moments located on an atomic lattice. This is true. Second is the magnetization tends to lie along easy directions determined by crystal structure, atomic scale texture or sample shape. This is also true because they have a particular easy axis orientation that depends on various factors, and the magnetization always tend to lie along that direction. Third is that heating even above a critical temperature known as Curie point does not affect the spontaneous magnetization. Now this is not true because you know that if you go beyond Tc, T greater than Tc, then obviously you will be crossing your ferromagnetic regime. So you will be converted into a paramagnetic regime where no spontaneous magnetization will be present. So it will be coming from ferromagnet to paramagnet phase transition. So no spontaneous magnetization in a paramagnetic phase. That is why in spontaneous equal to 0 in paramagnetic phase, that is T greater than Tc. That is why third option is false. Okay. Third option is not true, so this is your correct option. And the fourth was that although there is no reason in principle why uniform ferromagnetic liquids should not exist, it seems that there are none. This is also true. So the only option is left is 3. So with this we complete the week 5's tutorial assignment, and if you have any doubt about this you can let me know in the discussion forum or in the video comment lectures, whatever.